I decided to do something which is perhaps unusual for someone who's on the job market, and I'm going to talk a lot about things that I didn't do and just review what's been going on in this field. And if I have a little bit of time at the end, I'll give you a flash slide of things that I've been doing. A lot has happened in the last 5-6 years in the topic, and I get asked tons of questions about how these kind of particle physics, collider physics tools have been useful for gravitational wave physics. And so I thought I would just kind of cover the story. I'll start with a superliminal advertisement, points if you get the Simpsons reference. Then I will quickly talk about just kind of the general overview of perturbative approaches to gravitational wave science. Then I will actually talk about some of the results that have been coming out, and hopefully I have time, I'll give a little mini lesson. So I'll show some equations, use some toy Feynman diagrams, and actually explain how Feynman diagrams are useful for this problem. So you don't have to understand any of the equations or even look at any of the equations. I'm just pointing out I had a paper released today where I studied the perturbative dynamics to two-loop order and all orders and velocity. So this is the post-Minkowskian expansion, and basically any gravity theory that you want. So arbitrary number of scalars, higher dimension operators, up to dimension 6 operators when you include the scalars, and then I concluded gravity operators up to dimension 8. But I'll return to that if there's time. But I just wanted to advertise it in case this is the kind of thing you're interested in, and it's on archive right now. Great, so as we've heard a lot about, there are black holes, we know they're there, and we know they produce gravitational waves. We have Einstein's equations. We'd like to compute waveforms and compare with what we see. I wish that question mark was easier to fill. Now, in an ideal case, so just solving them analytically outright is not going to happen. In an ideal case, you just throw them on a computer and you simulate every single set of parameters that you want, and you produce every single waveform that you want. But in reality, that's not going to happen. So that's a very useful thing because it would be exact, tells you about strong field physics, but it's a very computationally expensive thing to do. In particular, you have limited durations and limited parameter spaces. So if you have black holes that are extremely widely separated and you're really early in the in-spiral, or there's a hierarchy of mass scales, this isn't your best approach. So in practice, this is supplemented by analytic approximations. Analytic approximations are performed, but they're approximate, they're perturbative, and so in practice, they are resummed in some kind of phenomenological model. The one I'm more familiar with is effective one-body models. What you do is you inform these phenomenological models, which have a bunch of tunable parameters, with things you know from NR and things you know from perturbation theory. You then have a model which is very quick and powerful, and it can, in principle, cover a wide parameter space. But it needs tuning. So here are some of the perturbative approaches that people use. The most immediately relevant approach for the quasi-circular or not extremely extremely eccentric orbits is the post-Newtonian approximation. So we've heard about this already. That's when you use a virial theorem to relate v squared on c squared to gm over r. And you basically have some kind of weak field or non-relativistic expansion. And OK, 0pn, that's Newton. 1pn, that's Einfeld-Hoffmann. And successive orders have been computed. And I will highlight a lot of work has happened in the, say, 2010 plus era, and that has to do with things I'll be talking about shortly. I will also caveat, there has been basically comparable progress with effective field theory from more standard post-Newtonian methods. You don't have to use effective field theory. And I don't want to discount any of that work, but I'm not going to be talking about it today. I'm just going to be talking about the effective field theory approaches. And I'll highlight one place, or a couple of places where effective field theory has proven to be more useful. These asterisks are just saying that there's partial results at that order, but it's still quite an incredible set of calculations when you consider the fact that the number in post-Newtonian order effectively counts loop order in some Feynman diagram. And so these are extremely high order calculations. The thing I have been involved in is the post-Minkowskian approximations. So that's when you do perturbation theory in G Newton, but you can retain an infinite order in velocities. This is particularly useful when if you have a scattering orbit, so you're way out here, then it's useful, of course. I need all orders of velocity. But even if you have something that's bound but very eccentric, it can be particularly helpful. And there's plots to support that. OK, so here's a story. 2019, when a collection of particle physicists, people who compute scattering amplitudes for a living, really got involved in this, they computed something perturbatively. They found an effective Hamiltonian perturbatively into 3 p.m. order, so order g cubed. That is these quickly departing dashed lines away from the cyan line, which is a numerical relativity prediction. This is binding energy as a function of effectively the number of orbits you are to merger. And you can see that they're bad. They were then imported into one of these effective one-body models, which are these solid lines. And you can see that they're better, but they're obviously going to be bad as you get close to merger. But I don't know, maybe around 5, 10-ish orbits to merger, they're still doing OK. LIGO scientists said, hey, amplitudes practitioners, thanks for your interest. This is great, but you have to do better. If you do better, we'll incorporate it into our models, and we'll see what we can do. Fast forward to this recent December. Bonanno et al., who was one of the authors of the first paper, took the state-of-the-art in post-Minkowskian calculations. In this plot, they didn't show the perturbative calculation, just the resummed, so the informed effective one-body model. That is this, and this one is flipped. And that is this, say, red solid line. And underlaid just underneath it is the NR line. And so now you can see we're deep into one cycle to merger. This is actually working quite well. To quote them, I'm not going to read the whole quote. Effectively, these PM, post-Newtonian informed resummations, are outperforming some classical PN resummations, which have historically been used for generating waveforms. And so they've responded back saying, you know what? All right, this is a watershed moment. These QFT methods are becoming actually, they're relevant for production level waveforms. And here's an example of a waveform that they generated. That's an overlay on NR. It's incredible. I won't talk about that, but if you're interested in gravitational self-force theory, there's an additional resummation tool that's come from that doesn't require building an effective one-body model. And you just effectively Pade resum the behavior of these scattering amplitudes to account for the fact that there's a separatrix where at a certain impact parameter, I will plunge into a black hole versus continue to do a zoom whirl. If you just build that into the perturbative data, you start to match NR, or at least match self-force extremely well. So, OK, that's kind of doing this talk in a reverse order. That is what's been going on. That's the data. This is working well. Now let me explain the actual ideas. So here's 2 black holes. They're very close to each other. We can't do anything here. If we make them a little bit further apart, I've just pulled them apart. It looks like they got smaller. That's funny. If I pull them even further apart, it looks like they got even smaller. This is just the intuition that when there's a length scale, a large length scale in comparison with the Schwarzschild radius, the objects look like point particles. So that's going on here. So the idea of EFT for compact objects is to literally replace those objects by point particles and do computations. To do properly requires careful thought, effective field theory tools, matching calculations, et cetera. I will get to that if I have time. But if you're taking nothing else away, zoom out, they look like point particles. But we can also zoom out further. So now I'm not moving the bodies away from each other. They're still separated by, say, 100 GM. But I'm just literally walking further and further away from these black holes. Walk even further away. This red line is, say, gravitational radiation. And you can see that if I'm sufficiently far apart, the binary itself looks like a point particle. And on this scale, I can now resolve that gravitational radiation. I can see the different wavelengths. And so this is just a statement that the typical wavelength of the radiation is much longer than the actual orbital radius. And so there's another place where you do a compact body effective theory where you replace literally the entire binary by point particle. Really, it's a dynamical set of multipoles living on a world line. So what happens when you do this? OK, I've kind of mentioned this already. We have, say, a Schwarzschild radius, which the radius of my compact object might be comparable to that. That is much smaller than a typical orbital radius, which you can estimate just from a virial theorem. And that, again, is much smaller than a typical gravitational wavelength, which just comes from the period of the orbit. And so you have this hierarchy of scales, and at each step in the hierarchy, you want to simplify the problem maximally by replacing the stuff that's compact by just a worldline effective theory. There's a number of things that go into this. I won't go into all of the details, but one thing you do, you say, okay, I have a couple of bodies. Let's describe each of these bodies by a worldline. Now what I have to do is perturbation theory to work out the effective gravitational potential between these worldlines. So all these computations are effectively just done in flat space. The bodies are well separated. The gravitational field between them is a perturbation of flat space. And so you have a set of Feynman diagrams to compute to work out the effective potential between these bodies. You also work out the effective multipole moments of these bodies, the way that they source radiation, by computing analogous diagrams. Once you understand the dynamics of those multipoles, you match that onto some effective single body theory, a zoomed out single body theory, and you compute the radiation from that. And even that computation is non-trivial because that radiation that's emitted from this effective single body can backscatter off of geometry and do very interesting things. Just as an example, here's some graphs from a 4PN calculation to compute the effective potential between the bodies. Here's some graphs that show you how the multipole moments can change because it's not just the masses that source radiation, but radiation can also couple to the gravitational stress energy itself. Here's some of those actual computations of the radiation waveform, where you can see there's multiple backscatterings, there's gravitational memory effects, there's tails. All of this is built into these diagrams, hereditary effects, if these words mean anything to you. And for the more particle physics people in here are another set of diagrams that are describing the same physical process, but they actually lead to an RG running of the effective mass of the binary. So all the tools that you think would show up when you're doing these loop calculations really do rear their head. Should also say, in more conventional methods, you have this intuition in position space of a near zone and a far zone. And the way that's implemented here, when we don't have geometry, we just have Feynman diagrams, is into something that's referred to as a split into regions. So you identify certain momentum modes for the gravitational field. So all of the time scales are set by the orbital period, but the length scales are different for the two. This is something I'd already mentioned. And so the so-called potential modes, the things that contribute, the modes of the gravitational field which contribute to the binding energy, these have a particular scaling in momentum space. The radiation modes have a different scaling, and that lets you cleanly separate out the two effects when you're computing loop diagrams. Now, I don't have time to review the full history, not at all, but I wanted to hit some of the main highlights. So the real application of these effective field theory ideas to this problem was by Ara Rossi and Walter Goldberger in 2006. They coined it NRGR for non-relativistic general relativity, building on ideas from NRQCD and NRQED effective theories. Shortly after that, there was a burst of activity. People added spin to these bodies, absorption effects. They properly treated radiation reaction. They found good variables that let you effectively reduce the loop order for certain calculations. Tons of work. I could not account for all the authors. Reproducing 2PN, 3PN results. Another extremely important contribution came in 2017, where there was an ambiguity in the conventional literature regarding how certain 4PN calculations should go. I don't have time to get into the details, but effectively there was simultaneously UV divergences and IR divergences in a calculation, and it was not clear from conventional methods how to write down an ambiguity-free expression which eliminates those divergences. And from the effective field theory point of view, it was actually completely obvious there was no room for ambiguity. And so they were able to predict the correct result, which was completely corroborated by matching in the conventional theory to things coming from gravitational self-force. So it was a consistent story, but in EFT, you didn't need external validation. Since then, people have continued pushing to higher orders, especially high orders in radiation reaction problems and spin. And I'll leave it at that because I have to move forward. The extension to post-Minkowskian ideas, I think, are conceptually very interesting. So Ira Rothstein and his student Duff Neal said, this is so completely separate from worldlines. I will return to worldlines shortly. They said, wait a sec. From a particle physics point of view, Lorentz invariance and unitarity basically just completely dictate the form of graviton scattering amplitudes. I don't need to know anything about differential geometry or Einstein. I can just tell you the way that gravitons have to scatter. In fact, I can bootstrap these. I don't have to write down an action. I don't have to write down Feynman rules. I can just write down the amplitudes because they're sufficiently constrained. And so the same is true for scalars coupled to massless spin 2. And so what they said is, in principle, one should be able to compute these scattering amplitudes, just from a bootstrap perspective, and match to some kind of effective potential for a particle moving in a background, so a particle moving in an effective metric. They did this at leading order, and they discovered, without solving Einstein's equations, at least the linearized short-shelled metric. The main lesson to come from that work that really started to drive this field is maybe we shouldn't be computing things like potentials. Potentials are notoriously gauge-dependent, subject to some of these ambiguities that I mentioned before, and they're inherently they're natural for a non-relativistic expansion. But if we have fully relativistic data coming from scattering amplitudes, perhaps we should do something else. We should just compute a fully relativistic gauge-invariant quantity, like a scattering amplitude. This was then realized to one-loop order in 2018, and that got a lot of particle physicists and amplitudes people interested in the problem. The real push, the real thing that set this off, there have been conferences since. Half of amplitudes was dedicated to gravitational waves recently, was this paper in 2019, that 3 p.m. paper. I had mentioned those results early on. Once resummed into EOB models, it wasn't quite good enough for data, but it was a proof of concept of these amplitudes ideas because it was a calculation that had never been done before with conventional methods. You really needed to use these amplitudes tools. Some of them, I will just point out, involve things that might sound crazy, like taking gluon amplitudes and then squaring them to get graviton amplitudes, using unitarity methods, so gluing together a bunch of different scattering amplitudes in weird ways to construct loop amplitudes. They used, basically through the whole book of what we know from collider physics on how to compute amplitudes, threw that at the problem, and they were able to do something that other gravitational wave theorists had not been able to do previously. I can't cover all of the results that followed in the couple of years after that, but everybody got excited, basically. But really, people accounted for spin, absorption tides, computed waveforms, fluxes, tons of other things, and there's already a review on it in just a couple of years. A very important follow-up to this was the 4 p.m., so that's now a 3-loop calculation using the same methods. I'm going to fast forward. State of the art is now 5 p.m. Sorry, partial results at 5 p.m., so the 4-loop calculations fully relativistically. But I will highlight that along the way, people who are more used to working with worldlines, so that's where we started with all this, said, it's great, we've learned a lot about how to do these calculations, in particular how to evaluate these multi-loop diagrams fully relativistically. That's very useful for us. But ultimately, you're computing something that's quantum mechanical in nature. It's a scattering amplitude. Is there a way to use what we know from just classical worldline theory and incorporate some of these insights from the quantum mechanical scattering amplitude theory to efficiently do these computations? And indeed, Porto and Plefka, their groups created what we call a PN EFT or a Worldline QFT approach to the problem. And they are the people who've actually really pushed the 5 p.m. order. And I myself am a Worldlines guy. So I don't have tons of time to do all these things, so I'll carry over a lot of my mini lesson into the discussion session, I guess. But I wanted to address just some common questions that I get about this. Question number 1, how do Feynman diagrams show up in classical physics? Isn't this something that you do when you're literally describing infinitesimal particles bouncing off one another? And I wanted to say that this is actually the kind of combinatorial structure of Feynman diagrams is really just a completely general thing that happens in equations of motion with waves, and it's just telling you about something about locality. So here I just have a simplified cube theory with a source, has an equation of motion, and I'm going to treat this coupling G perturbatively. And I'm going to just solve for my field perturbatively in G. At leading order, I just have box phi, so it's the D'Alembert is J. I invert it. I just have some Green's function, and I can just draw a little diagram to represent that that Green's function propagates me from J. I integrate over all the places that J can be to here. At next order, phi starts to source itself. I can, again, invert this. I have some weird kind of looking expression with a bunch of box inverses, a bunch of convolutions of Green's functions. What is that integral really doing? Again, if I just follow my logic that these Green's functions are represented by lines and points are things that get integrated all over space, I can write that in this simple way. Again, higher order, same structure. Nowhere in here did I say anything about point particles. I'm just solving a classical physics wave equation perturbatively. Okay, that was just solving the equation, but what if I wanted to compute something like an energy? So if J represents, say, two masses in gravity, then you would compute their energy of that configuration of J's. That's literally how these effective potential calculations are performed. You just take the Hamiltonian for that theory, you plug in your solution order by order, the different terms in my Hamiltonian. Say this one, for example, you plug in phi naught, has this diagrammatic representation. You go ahead and you do the integrals. Going to one higher order, you get these, again, these closed diagrams. You do the integrals. If I wanted to now I specify to point particles. I say, OK, let's let J just be a sum of two delta functions. So I just have two world lines separated by some distance, one at x1 and one at x2. Plug it into these equations, compute the energy. You find a set of diagrams. Maybe I'll probably won't have time to revisit these ones. This one here, where you actually exchange the particle, you can compute the integral, and you find, oh, that's the Coulomb interaction. Great. I have a set of corrections, and I have an infinite set of loop diagrams that describe my corrections. In gravity, we know that the whole story is not just the Newtonian or the relativistic version of Newtonian field. There are nonlinearities. And so all of the interesting stuff comes from these corrections. And that's really what we work to compute. No. Save that for the discussion. Yeah, so just a note on why do we get to effectively describe these compact objects as point-like sources. This is my dog, Onyx, watching me cut my wedding cake. I had to crop me out. He's a complicated system whose dynamics I don't fully understand. But if I want to probe him from long distances, say distances much longer than this length scale LUV, then I can effectively describe him, effectively having a specific mathematical meaning by a point source inside of this. So sorry, let me say this differently. If I want to understand physics at long distances, so distances longer than this scale LUV, what I get to do is get the physics kind of wrong inside of this scale, as long as I match certain long distance properties. If you do a multipole expansion, you're doing this all of the time. So what I have to do is I have to replace Onyx by some point particle. I have to make sure that point particle has certain couplings to the fields that I'm interested in, and that it has couplings that I have to perhaps match by doing some calculation which actually understands Onyx. But without knowing the values of those couplings, Wilson coefficients, no relation, I can still make predictions for the behavior of Onyx's interactions with long-range fields. And this is not just something that happens in particle physics when people do RGE, renormalization group, regularized infinities. This is always happening. We are always doing this. Whether you're doing classical field theory or quantum field theory, there is always a short distance cutoff inherent in your calculations. That's what that last slide about Maxwell theory was. When we write down that the divergence of E is equal to electric charge times a delta function in every electrodynamics textbook, we don't actually mean that the electron is point-like. Sorry, we don't mean that it is a point. We mean that it's point-like up to some scale. The trick that lets you get away with doing all these things successfully is you want to get the physics wrong in that region in the most convenient way. And in gravity, that's dimensional regularization, but I don't have time to really go into details because apparently I'm out. So I'll save all of that for discussion. Effective field theory allows us to understand divergences where they show up, systematically account for finite size effects. That has to do with the thing I just skipped, unfortunately. But really what it lets us do is use effectively point particles in flat spacetime and do perturbation theory. And we're very, very good at doing that because particle physicists over the last 100 years have developed 70 years have developed tons of tools, bootstrap tools, momentum space Feynman rules, dim reg, renormalization group, field redefinitions, and perhaps most importantly for recent calculations is incredibly powerful multi-loop integration softwares that people at CERN have been developing, or people who work to compute things for CERN have been developing for years. So with that, I'll thank you. And I'll just leave a bunch of things that I've been doing that are related to this on the board.
Thank you very much. Questions from the audience?
So maybe in the middle of your talk, thank you. You discussed recent results in post-Minkowski, like 3 and 4 order. You said you could do spin. Is that arbitrary spin, or is that like small spin, or
great question.
Interested in?
Yeah, so it's done perturbatively in spin. So I should say, at tree level, I believe people have been able to do calculations with arbitrary spin. So they found interesting ways to resum the perturbative series in spin. I don't think that has been done to loop level. I can't remember, but definitely not beyond one loop. But there's this power counting that the effective spin parameter power counts kind of like the Schwarzschild radius. And so for expanding in G Newton anyways, you should be expanding in spin. So even if it's a rapidly rotating object, because we're doing perturbation theory, you don't need to track the contributions of spin to arbitrarily high order.
I see.
I was wondering if you could say a bit more about the comparison between the waveform and the SUVNR benchmark that you showed. I'm particularly curious about the merger regime. I mean, you mentioned traditionally this is done with some calibration to numerical relativity because you do have this scale separation breaks down, right, when you have the merger unit. So is it true that there's no numerical calibration to the FT waveform? Like how is the merger and the ring down attached to the spiral in that case?
That's a very good question, and I unfortunately don't know the answer. It's definitely the late stages of that are definitely not informed by perturbation theory. That's some black hole perturbation theory, quasi-normal mode matching, I believe. But I don't actually understand how they do the gluing. Sorry, that is an extremely relevant question, but I don't know.
Yeah, Iris.
So you said you can treat the binary mass as running, just to release the calculator. I'm just curious, how does it run, and what happens as I approach my scale of the binary separation? Like, does it blow up, or like what happens?
It's a great question. The mass is larger. How do I say? The effective mass is larger as I go to longer distances. And that's because basically gravitational radiation backscatters off the geometry and remains trapped near the black hole. And so as I go to larger scales, I basically have more of that radiation trapped in that region. And so as I shrink in, I start to see more like the bare mass.